Are we ready?
Ready. Perfect.
All right, so my name is Eric Martindale. I work for BitPay. As per Robert's introduction, I am their Chief Developer Evangelist. My job entails basically going out into the community and seeing what engineers and developers and startups and entrepreneurs are building and what they're wanting to build, and taking that feedback and making sure that the things that we develop at BitPay are meeting their needs. So BitPay, if you haven't heard of us already, we were founded in 2011 in sort of a very early stage in Bitcoin's life. We've seen a number of bubbles and a number of crashes, a number of exchanges come and go. So we've been through the storms, right? So we've had to, all throughout this process, have had to build and maintain enterprise-grade services for larger customers who you may more recently have heard are now accepting Bitcoin, such as Microsoft, Newegg, Tiger Direct, etc. It is extremely important that they have high-level services that stay online. So throughout the number of years that we've been around, we've developed some tools that we've completely open-sourced because we feel, and we recognized very early on, that the only way to true and genuine security in software is for it to be open source. All bugs become shallow with a sufficient number of eyes. Subsequently, when you're dealing with finance and especially things like Bitcoin, where they are the future of all of finance and many other things, you want to be absolutely certain that things are secure. So BitPay has invested very heavily in the open source ecosystem. Today they're led by a couple of flagship products. Bitcore is one of them. And that's what I'm going to largely talk about today, and then show some of our future plans for what Bitcore does. So Bitcore is the very root of everything that BitPay is building, including our open source multi-signature wallet, Copay. It provides a utility library for creating and signing basic transactions, creating multi-sig outputs, and even inserting data into the blockchain. So just some basics about why we made some decisions that we did. First of all, it's in JavaScript, largely because JavaScript is perhaps the most widely used language in the world. It is the most accessible. Whether or not it is performant is another question. We believe that it is and will continue to become increasingly performant. It's just simply the most accessible. You have so many engineers and so many developers out there who are familiar with JavaScript constructs, with and without all of its little bumpy edges. Furthermore, it lets us be isomorphic, which means that we can run the same code everywhere. This is often considered a pipe dream up until very recent days through the development of Node and also a lot of the client-side developments in the browser space. You can write the same code, execute it, and predictably get the same output. There's a couple of gotchas to this, and we might cover that a little bit later, but for us it serves a really good way of spending our engineering time. One of the things that's really important to us, as I mentioned with enterprise-grade compatibility, is test coverage. You can never be sure that your code is any good at all if you don't have adequate test coverage. So we're slightly ashamed even to not have 100%, but we do have 97% test coverage. We have a rule with our commit messages, and when you start talking about managing open source projects, this is a really good thing to do, is any pull request that gets accepted into an open source project, we have a rule that it must increase code coverage. Right? If you're going to be introducing new code, your code must be covered in addition to potentially increasing coverage in other areas of the stack. Furthermore, pursuant to the same goal of having good test coverage, we basically took all of Bitcoin Core's fixtures, the test fixtures, and passed them into Bitcore. So we know for sure that we have as close to bug-for-bug compatibility with the blockchain, with the Bitcoin Core reference client as possible. This is very important to us. So let's talk a little bit about transactions. How many of you in the room know what the required parts of creating a transaction are? All right, what are the required parts of a transaction?
The inputs, the
the addresses that you're going to take from and output to, and the hash of the transaction and signatures.
That's correct. You've got the inputs, you've got the script for the outputs, and then you've got the amount, basically. What are you moving? And of course, the signature must be provided for that to be valid. So everything that we're going to be doing is based on finding unspent transaction outputs, because the way the blockchain works, every transaction has a series of inputs and a series of outputs. Those outputs basically float there. I like to think of this as a model of there are no real Bitcoin. They are only locked up into potential energy, right? They don't exist on your computer. They don't even really exist in the blockchain. They're not an asset that's really moved around. You're basically moving potential energy, reallocating that potential energy in the blockchain. And this is stored in a global set of transactions that have not yet been spent, called the UTXOs. There's a couple ways to get these. The first of which is, of course, in Bitcoin Core, you can go into the RPC console and just type in list unspent. I hope most of you have at least Bitcoin Core running on your box at some point. You can also, in Bitcoin Core, use dump priv key to get the address from an unspent transaction to just go ahead and get that transaction. And this will generally be a hex-encoded version of your transaction. And furthermore, and maybe an easier way is through a REST API that a couple companies offer this, but we have it on Insight. If you guys go to insight.is, we've got a whole blockchain explorer that gives a list of addresses and their UTXOs. And that is at the endpoint /API address, the address, and then the /UTXO, which will provide you with the output set transactions that you could use. So, as I kind of talk through a couple of these things, I would encourage you to just go ahead and pull up Bitcore Playground, bitcore.io/playground. This is it's an in-browser REPL and built-in documentation site that will allow you to basically peek and poke at the different constructs that I'm going to be building with here. That again is bitcore.io/playground. All right. The most basic thing in Bitcoin is your average person-to-person transaction, right? In Bitcore, and specifically, we're going to use Node.js here as an example, but this all works with require.js in the browser as well. And in your Playground, this should all automatically be built in for you. Obviously, using Bitcore is pretty simple in terms of getting it. Bitcore require Bitcore, and we're going to create some convenience functions here. Like transaction, which is a class exposed, address, private key, and unspent output. Most classes in Bitcore are extremely consistent, meaning you can instantiate them using a basic constructor, new, the thing you want to construct, and then pass in a variable. That variable can be a number of things. We accept both hex, with format, base 58 encoded versions. The library will automatically attempt to figure out what the type of string you're passing it in the constructor is, and will generate that type of object for you with all of Bitcore's convenience functions. You'll see this in creating a change address. We literally pass in an address that we know that we have a private key to. Similarly, private key, I'm actually going to call explicitly from with format here. So if you have a with encoded private key from any of your other pieces of software, you can import it directly into Bitcore in this way. We're just going to go ahead and instantiate an instance of a known unspent output. This is in the blockchain. I believe it's on testnet 3 if you want to go and investigate this specific transaction ID. You'll notice that it's the required parts, transaction ID, the address, the pub key, script pub key, and the amount, right? So to create a transaction, we need to have this UTXO as an input to a new transaction that we're going to create in broadcast. Well, we also want to know where is it going to. So we're just going to go ahead and instantiate a new destination. Same thing, you'll notice that this address is different from the previous one. And then we're just going to use a simple chainable method, transaction, to create a new transaction. You can call .from, which will take in your UTXO. You can call to, which will be a destination, and an amount. And this is the only part that I have ever seen someone get caught on, is if you do not specify a fee, the remainder of the balance from the UTXO will be associated with the person who mines the transaction. So, be mindful of your fees and make sure you're spending your UTXO. And specify a change address. As you can see, .change, and then we sign this subsequent transaction with .sign. We simply provide the private key. This will return a completely valid transaction. I'm just going to make it a little bigger for those of you in the back who may or may not be able to see.
Can I just ask a question?
Of course.
So, if you don't, you're providing a change address, and you said if you don't include a fee, then the rest of the unspent goes to the miner.
Can you repeat the question, please?
So he's asking. He's basically asking for clarification. If you in Bitcoin, if you create a new transaction, and the amount that you're including in the transaction is not the total amount of your input UTXO, that will be considered a fee on the Bitcoin network, and the miner will be able to grab those fees.
Yeah, but you can't add a fee of 0.
You can also add a fee of 0.
And you've already got a change address to say where the change should come back to.
That's correct, but the Bitcoin network will, if you do not spend the full amount to the destination pub key, then it is considered a fee by the network. It's just a...
I know. I just thought it might be a specific of this implementation. If you miss out that fee, I would have thought that you would put a 0 fee in so that you don't lose all your Bitcoin.
Possibly, yes. We also wanted to go ahead and get this block put in the blockchain. We didn't want to wait around for this one, but broadcasting is very easy as well. You can serialize it out to the hex format that Bitcoin Core will expect, and that command in Bitcoin Core is simply send raw transaction. Now, Bitcore also offers the ability to connect to the RPC network and broadcast the transaction itself. For simplicity's sake, I'm going to cover that later. Any questions so far about creating and signing transactions? It seems pretty simple, pretty straightforward, I hope. Now, Bitcoin is far more interesting than the currency aspect of things, as I'm sure that you guys have experienced throughout some of these other segments. There's Ethereum, there's a number of different ways of using the blockchain for storing data and using that data in interesting and clever ways. Counterparty, proof of existence. If you haven't heard of proof of existence, it's simply the hashing of a document, pegging it to the blockchain, and signing it with a key that you possess. So the first one that we're going to go through is a miner fee with data, which is basically you're going to create a small Bitcoin transaction and then incentivize miners to go ahead and mine it to include it in the blockchain. And so you'll be able to retrieve that data later in the future. Here you'll see a very familiar interface with unspent outputs. You'll see the same information that we had in a previous transaction, the amount that we'd like to move. We're going to create a new private key, create a transaction from the unspent output, set our fee, and there's a method called add data, which lets us add any arbitrary data. Up to 80 bytes, of course, or now it's 80 bytes, it used to be 40. And then you create and sign that transaction, and you end up with an actual transaction ID that you can broadcast on the network. It is literally as simple as transaction.add_data and the string value of the data that you're looking for. You can call this multiple times, create multiple transactions to include larger amounts of data.
I think it's brilliant, the add data. But I'm looking at the unspent output. That amount, is that in Bitcoin?
Yes, that is in Bitcoin.
So other return object, or JSON return object, or API is in Satoshi, so if it was mixing up here, it could be a disaster, right?
You could have a disaster, absolutely. Everything is stored basically in pure Bitcoin in Bitcore. We also have a unit conversion. Everything is actually an instance of a unit. So you should always be able to check the unit that you're using and verify that you're not spending Bitcoin when you intend to spend Satoshi, right? Always, when working with anything financial or anything technically financial like this, take responsibility for your decisions, double and triple check your work, and work on testnet. Don't do this with live transactions unless you are really confident in your code. So we're going to go ahead and take that object, take that transaction and cast it to an object. And this is what that transaction would look like. For those of you who have been reading about how Bitcoin's scripting language works, you should see the very familiar output down here of the op return, the number of bytes, and the actual hash of the data. All right. The script is encoded as hex above, let's see. We have the change address, we have the array of inputs, which is the array of the unspent transactions, and then the outputs, which are signed scripts that contain the data that you just used via add data.
And what were you hashing the text with, the data with?
This is, what are we hashing it with?
Yeah, so it was hello world, and then you've hashed it. How did you hash it?
I don't recall in this specific case. I think you can find it in the documentation. .add data will describe exactly how it hashes it.
It's a UTF-8 encoding.
UTF-8 encoding? Okay, great. Another case of this is multisig with hash data. This is sort of like the next layer on top of that, where we can have multiple keys, and we hash that data, we sign it with a private key, and we store that in the blockchain, and thus it is retrievable with the possession of our private key. This is using multisig. You'll notice that we provide some of these basic hash functions like SHA-256, RIPEMD160, which is everywhere in Bitcoin. We're going to create a new buffer from our data, cast it to a hex string, and that's what we're actually 256 RIPEMD hashing. We're going to create a new private key from that data hash. Okay, this is basically the only way that you can get this private key is if you know the data that was input originally. We'll get the public key that corresponds to that. We're going to go ahead and create a transaction with this. We're going to use, again, the familiar unspent transaction output that we have from a previous transaction. From our unspent, set our fee, and then we're going to do something new called add an output. All right, this is a new output class, and you'll notice here that there is a build multisig out function, which will take an array of public keys, and then a secondary parameter, which is the number of those keys that need to sign this transaction for it to be validated. All right. So we're going to go ahead and sign that with one of our private keys, or the private key for the previous unspent transaction. We'll serialize it, and we actually get a real transaction out on the Bitcoin blockchain. This is useful in a number of ways. I think Counterparty originally started doing something like this. They may have moved on. They have moved on to another solution. But this basically allows multiple parties to coordinate with similar data and verify that it's basically a messaging scheme across the blockchain. Cast it to an object, and this is what it looks like. You get an op1, which is anyone can spend. That's op true, basically. You get the hash, you get the next hash, the next public key hash, and op2, and op check multisig. So what this is going to do is it's a basic multisig transaction, of which you can only retrieve the transaction if you actually have the data. I think this is where Counterparty is right today, and this is pay-to-script with hash data. Very familiar. We're going to have an array of data though this time, and then for each of these pieces of data, we're going to create a multisig output and do basically 4 of the 5 that are required to spend this output. Same thing. We use unspent outputs. Create a transaction class from our unspent output to our destination, which if I hop back up here, our destination is that multisig output, which is a 4 of 5 multisig. And then we get a transaction hash, and this is what that looks like. We have 2 outputs now. One is the actual fee here, and then the other is the multisig address. You can also encrypt data and use multisig to retrieve that data. This is actually pretty much directly lifted from another implementation. It uses the arc4 compression. You basically take input data, you arc4 compress it, and then you encode a string. You basically take the cipher of that string, and you create a public key from it. The other interesting thing here is that we're actually prefixing that with the 02, which signifies that it is a public key, and then we create a public key from those hexed outputs, and we go ahead and do the same thing we did before, create a transaction, add an output, sign it, and serialize it, and we now have a transaction again. This is really all just to demonstrate how easy it is to do these different types of things in very small amounts of code. All of the things that Counterparty is doing, in different types of embedding data on the blockchain, you can all use a very common interface to do these things. And that is really the objective of what we're looking for with Bitcore. Some other notes when you're doing these things, something that we ran into was that 0 output payments to a public key hash is non-standard. It's really considered dust. But with op return, you can actually set it to 0 because it means anyone can spend. Or it's unspendable. So I want to talk a little bit about what Bitcore also offers. So Bitcore is the basic framework that has your transaction class, your public key class, your hashes. Where the real power of Bitcore comes in is in its plugin architecture. And we've already seen a number of people sort of developing various plugins for this. Insight is one such plugin. We have a full node version of Bitcore in the works right now. It's public on GitHub. And we even have the wallet server implementation for Copay is built entirely using a Bitcore plugin. But I'm going to talk about 3 specific plugins because I think these are the ones that really open opportunities to build a lot of other things. The first of which is Bitcore Channel. This is the payment server implementation purely using Bitcore. And it exposes a class for both server and client, or consumer and provider, which is really useful for very small amount, high volume transactions. Bitcoin itself is already pretty good for micropayments, but when you have a case where you have a very high volume, such as you're trying to pay per kilobyte or even per megabyte of data transfer or per message in a chat application, you're not going to want to spend 3 or 4 cents per transaction to broadcast that. Instead, you're going to want to aggregate them into a special thing called a payment channel. And I'll get into that in just a moment. Bitcore Payment Protocol. I was talking a little bit earlier about the isomorphic nature of Bitcore because it uses JavaScript. Bitcore Payment Protocol is a plugin that extends Bitcore in such a way that you can completely construct and validate a payment protocol request, including the certificates, in client-side JavaScript.